Hi, it's Miss Molesbury here, and today we're going to go over AP Pre-Cal Lesson 2.2. It's all about change in linear and exponential functions, and it's going to feel very familiar because it is building completely off of what we just did last class in 2.1, talking about arithmetic and geometric sequences. So here are the goals for the lesson, and we can see if we accomplish them by the end. So our goal is to compare linear and exponential growth and practice representing these growth patterns with function formulas and graphs. I'm going to be honest, we're going to use more of the function formulas today, and the graphs are coming, especially exponential graphs. We'll be talking about that more next week and not, I guess not next week. Next week we're testing over 2.1, 2.2, but in the upcoming unit, we will be talking about graphing exponential functions a lot more. We're going to explore patterns in linear and exponential growth by contrasting ideas of constant percent change with a constant amount of change. So like a constant rate of change versus changing by a certain percent or ratio each time. So hopefully those are making you think back to last lesson as well. So let's take a look at the notes. In the last section, we learned that arithmetic sequences behave like linear functions. Let me grab my highlighter. So arithmetic sequences behave like linear functions, while geometric sequences behave like exponential functions. We're going to look more closely at the connections between the two today. So as far as arithmetic sequences go, last class we said there were two ways that we could represent an arithmetic sequence. We said that for a future value in the sequence, we needed the initial value or term 0. And then we needed to know D, the common difference. And that would help us find the nth term, where we could plug any value in for n, and that would add that common difference n times to figure out that term of the pattern. We also said if you don't know the initial term, you don't have to work to find it. You can use a different version of this equation. All you need here is, there we go. You need a different term in the sequence that we called the kth term. So this formula would be helpful when you have two terms in a sequence. Basically, we use a sub k as our starting value, and we determine how many times we need to use the common difference by how far away it is from our nth term. We're going to get more practice with this today, but then I want to put up some formulas you used in Algebra 1 so you can see how they correlate. Linear functions, you're familiar with y equals mx plus b. Here it's written as b plus mx, tying in with AP statistics like we talked about with linear regression. So here, instead of an initial term, we have the y-intercept, which is our initial term. It's 0, comma b. And then instead of a common difference, same idea, it's our constant rate of change, but it is our slope. And so you may have noticed when we were solving for the common difference, it's like we were using slope formula to calculate that last class. And then point slope form, when you did this in Algebra 1, you probably saw it written as y minus y1 equals m times x minus x1. That's how it's typed on the EOC formula chart. But then this is just another way to rewrite that. So it takes the arbitrary point on the graph, x, it's just saying x sub I, y sub I. So this could be any point on the function. And all it did was isolate the y. It moved that y value from the point over. So I'm going to go ahead and say xi here, and yi just represent a point on the function f of x. Okay, so you can see how these equations are very similar to your arithmetic sequence equations, where we have an x and a y, or a term number and then the actual term itself somewhere in the sequence. So very much related. Let's look at the same thing for exponential functions. So let me switch colors here real quick. Blue sounds good. Okay, so our geometric sequence, we said that if we know the initial term, or term 0, then it would be that value times r to the n power, where r is our common ratio. Oops, it's hard not to put an n on the end of ratio when after you write the word common. I don't know. Maybe it's happened to you too. So if we don't know the initial value though, we said we don't need it, we don't have to have it. We can instead, just with two terms in the sequence, go ahead and write a geometric sequence. We would have to have the kth term, so we would have kind of like the input, the term number, and then the actual value in the sequence for that term. That would help us solve for the common ratio, and we could write a geometric sequence, a formula for that. So the way that this is going to relate over to our exponential functions, you'll see to the right, you're familiar with y equals a times b to the x power. So here a is our y-intercept, so 0, a, and b is our rate. Or here, it's better, I guess, expressed here because the word rate doesn't really say what type of rate. Is it a multiplication or an additive rate? So it's written as an R here to remind us that it's related to the common ratio or multiplication rate. And then it does the same thing below. You wouldn't have really done this in Algebra 1, at least I don't think so, but we could write an exponential function in kind of like a point form. We don't have to know the y-intercept. We would just have to know that x1, or xi, excuse me here, and yi is a point on the function. Okay, so these tools are all at your disposal throughout this unit, and it will be at our disposal here in a minute when we work through some word problems. So we'll decide kind of what makes the most sense based on the problem. Okay, so summary, let's look at the similarities and differences between linear and exponential functions. It went ahead and just typed linear functions in slope-intercept form would be b plus mx. So we have our starting amount and then whatever our graph is changing by each time. So it says over equal length input value intervals. So that means equal length input value would be our x value intervals. The output values, so then we're going to analyze the y's, they change at a constant rate. And we know that our constant rate is going to be our slope or our common difference as it relates to sequences, arithmetic sequences, and therefore the change in y is based on addition. Even if that means you're subtracting, then we could say the common difference is negative or the slope is negative. Okay, for exponential, it gives the same formula from above, our starting amount, our rate, our multiplication rate, raised to the x power. So our input value is the exponent. So again, over equal length input value intervals, I should maybe underline that equal length, because we're definitely going to be checking for that. the output values change proportionately. Okay, so if you think about something that changes proportionately, like taking it back to, I don't know, maybe elementary or middle school, you might have talked about proportional figures where there was a scale factor, right? That's what you're multiplying by to turn something into its similar figure. So it's reminding us that the change B in this scenario in the y's is based on multiplication. So that's going to be our common difference, or not common difference, excuse me, our common ratio when we relate it back to sequences. Okay, so looking ahead at the last reminders before we actually do some problems, if you have 2 points, that's all you need to be able to write the equation of a linear function, an exponential function, an arithmetic sequence, or a geometric sequence. So let's look at some examples and see what it's trying to get us to do here. Example 1 says selected values of several functions are given in the table below. For each table, determine if the function could be linear, exponential, or neither. Okay, so the first thing I'm going to check for is if we have equal length input value intervals. So look at your x's and make sure I'm not trying to trick you by giving you unequal intervals or unequal length intervals. So just a quick scan of the x's tells me it's changing by 3, by 3, by 3, by 3. Great. So then I can go ahead and look at the y's and see it's always easiest to check for addition or subtraction first. I can see they are decreasing. It looks like they are decreasing by 2 each time. Okay, so for that reason, it looks like we have a linear function. So let's give a better answer here. Here we go. F of x is linear because the y values decrease by a constant rate of change and we could be really specific and say over equal length input value intervals. Okay, so that's our full reason. We've discussed how the x's are changing, or that we've analyzed them over equal length input value intervals, and that our y values, our outputs, are decreasing at a constant rate of change, or they change at a constant rate. We could, because none of the other examples ask us to, we could write the equation. But remember, to do that, we would actually have to find the rate of change here. So let's say we want to write the linear equation in slope-intercept form. Well, this table gives us enough information. We have that our y-intercept is 0, 7. So I could say that this equation is 7. And I'm not just going to do minus 2x here because although the y's are changing by 2 each time, we have to look and see what are our x's doing. So our x's, as the y's change by negative 2, our x's are really increasing by 3. So we would really need to do a difference quotient here, pick 2 of these points. Like I'm going to say 5 minus 7 over 3 minus 0. Or I guess we should say, let's take it back to unit 1 and say I'm going to pick the x values of 0 and 3. So I'm going to do f of 3 minus f of 0 over 3 minus 0, which would be 5 minus 7 over 3, which would be negative 2/3. So in my equation, the slope would be negative 2/3, and I would have 7 take away 2/3 each time. 7 minus 2/3 x. We could have written this in multiple forms. We could have written it as an arithmetic sequence instead, where we would have an initial amount of 7. We would have a common difference of negative 2/3. All right, but again, we're kind of going above and beyond what the question is asking. So let's keep going. We may do an exponential one just for fun in a minute, if we find one. So B says we have a table for g of x. First thing I'm going to do is glance at my x's, see that they have a constant equal length input value intervals, which they do, counting by 1. And then I'm going to look at the y values, and there is a pattern here. I am familiar with 0, 1, 4, 9, 16, and you are as well. But the question is, do we add the same thing each time? Do we multiply by the same value each time? And it doesn't look like we do. So if you tried to add, here we'd be adding 1, adding 3, adding 5, adding 7. So we don't have a common difference. Back from earlier in the year, you'll notice the second difference is the same, telling us that this is quadratic. If we wanted to check and see if it was exponential, we would have to check and see what are we multiplying by to get from term to term, and that wouldn't work. Like 1 divided by 0 is not possible. 4 divided by 1 is 4. 9 divided by 4 is not the same value, so we're not multiplying in order to get the next number in the output values. So I think we have determined that g of x is neither because the output values do not change at a constant rate or proportionally. So we checked for a constant rate of addition or multiplication. Neither one existed. All right, let's move on to C. So C has, it looks like we are counting by 2's. So we have equal length input value intervals. Then I'm going to go ahead and check my y's. So here it looks like if I tried to add the same amount each time, plus 1, plus 2, plus 4, not an addition, not a common difference. But if I look for multiplication, it looks like we're multiplying by 2, by 2, by 2, and by 2, which is great. So this, if it has a constant multiplication rate, that means that these values are changing proportionally. So this is an exponential function. So exponential because the output values change proportionally with multiplication over our equal length input value intervals. I wish there was a nice abbreviation for this. Equal length input value intervals. Okay. And then again, we could work to actually find the multiplication rate because remember, it's multiplying by 2 every time the x is changing by 2. So we could work to find the common ratio like we did last class. But we're going to have to do that down here in the next problems, and we're running out of space. So let's go ahead and look at D, and then I promise we will practice doing that. So D has an equal length input value intervals, adding 5 every time. And K of X, if I'm looking at the Y values here, they are decreasing. It looks like they are dividing by 2. So we could also divide to figure out that common ratio, or well, it wouldn't exactly be our common ratio since our X's are not counting by ones, but it looks like it's multiplying by a half. And so if we wanted to actually write the equation again, we could go ahead and practice with our geometric sequence formulas, or using, we could also use this formula here since we don't actually know the what am I trying to say? Oh, the y-intercept, excuse me, since the table didn't have it in there. So just for the sake of time here, let's do this. H of X and K of X are exponential because the output values change proportionally, showing we found that there is a pattern with multiplication over equal length input value intervals. Okay, so let's go ahead and take a look at. All right, so example 2 says, a wild rumor is spreading that Mr. Davenport won 3rd place in the World's Strongest Man contest. Oh, I don't think that's a rumor. I heard that too. The number of people that have heard the rumor can be modeled using a geometric sequence. Great, so the problem will tell you what type of pattern we're dealing with, where 43 people have heard the rumor on day 3 and 140 people have heard the rumor on day 6. According to the model, how many people to the nearest whole number have heard the rumor by day 10? All right, this is spreading like wildfire. So let's go ahead and look and see what we've been given. Instead of giving us specific term numbers, it's saying that each day we have a different amount of people that have heard the rumor. So if we want to think of these as ordered pairs, or as an input and an output, we could say it's geometric. We could say we have on day 3, our input is 43 people. On day 6, there are 140 people that have heard this rumor. It's geometric. We don't know the initial amount. So I'm going to go ahead, if we look back at our formulas, and use this formula right here. So I'm going to go ahead and write the formula first just as a refresher. Times r to the n minus k power. And I'm going to treat the first ordered pair as k and its output, and then the 6 as n and its output. Because right now, we don't know the common ratio. So that's our first goal. All right, so 140 people grew from the original 43. The ratio we don't know, and it's raised to the 6 minus 3 power. So if I'm going to go solve for r, I'm going to have to divide by 43. I have r cubed equals 140 over 43. And it does not look like this is going to turn out nicely. I don't have all my perfect cubes memorized, but I know 140 and 43 are not on the list. So we want to take the cube root of this, or we could raise it to the 1/3 power, either way. So in the graphing calculator, let me show you a couple things we could do. Calculator out. Okay, so remember under the math button, the fourth option down is your cube root. To make a fraction, it's the green button, y equals, and enter. And then I could type 140 over 43. Not a very nice number, so the common ratio is 1.482, etc. It's definitely growing. One trick, I can't point in this app, but just above the, I'm trying to think of what it is, second on. So just above the on button in your calculator, I believe, there's a store button, STO. So if you right now press STO and pick your favorite letter, I'm going to pick the letter R. So I'm going to do alpha and then the time sign. And my calculator now, anytime I type alpha and the time sign, anytime I type the letter R, it thinks I am using, I've stored that exact value unrounded in the calculator. So that is a tool that we're going to use some throughout this class. If you haven't seen it yet, now you have. We could also have done, let's see, make a fraction, 140 over 43, close those parentheses. If you raise that to the 1 over 3, the 1/3 power, you're going to get the exact same decimal. So if you'd rather write it as a fraction to the 1/3 power or as a cube root, either way, it's up to you. That's our common ratio that we're now going to go use to answer the follow-up question. How many people to the nearest whole number have heard the rumor by day 10? So now to find a future value, I'm going to say that it was 43 people and it's growing by 140 over 43 to the 1/3 that we've stored as R. And then it's going to be to the n minus, and k here was 3. So the n minus 3 power. How many days have passed since day 3? So let's go find on the 10th day, 43 times 140 over 43 to the 1/3, and then plug in a 10. Oops, sorry, my brain did 10 minus 3 and wrote a 7. There we go, 10 minus 3. So let's go to the calculator, type this in, and figure out how much this rumor has spread. Okay, so we have our initial 43. I'm going to do the trick of saying alpha multiply and raise that to the 7th power. So it should be rounding to the nearest, it does say nearest, so I guess I'll round up, nearest whole number, 676 people. But then again, if you do 43 times, and then you could either type it like we did on the paper, so let me make my fraction. Oh, there we go. Sorry, I remember when this app used to be like free and no ads, and it was so great. Okay, raise this to the 1/3 power, and then 10 minus 3, so times 7. Hey, we get the same 676 people. Oh, remove the ads by going pro. I just saw it say that. Well, that's okay. We can handle the ads. So 676 people. That's more than a full class here at Centennial. Okay, so hopefully that made sense. That would definitely obviously be a calculator question. I know it doesn't have a calculator symbol next to it, but you will have a calculator on this entire next assessment. Okay, let's do example 3. It says a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. Okay, so arithmetic sequence, we're going to be finding the common difference. If the 5th row has 31 seats and the 11th row has 49 seats, determine how many seats there are in the 25th row. So not as exciting as Mr. Davenport winning the, third place finish in the World's Strongest Man contest, but we can definitely apply our same knowledge and work with arithmetic sequences here in this word problem. So again, I don't know the initial amount, but I know that row 5, so 5 is our input, has 31 seats. And I know the 11th row has 49 seats. And so I'm using an arithmetic sequence. Oops. Excuse me. I said arithmetic and wrote an A. So the output of the kth term is going to be 31. And then I'm going to let in, oh goodness. Thank goodness for erasers. The nth term be my, here my 11th row has 49 seats. So my formula for any 2 points or any 2 terms in an arithmetic sequence is a sub n equals a sub k plus the common difference times n minus k. We don't know the common difference yet, but we will, because we're going to plug in 49 equals 31 plus the common difference times n minus k. So I'm going to subtract 31, and we have 18 equals 6 times our common difference. Okay, so it looks like here our common difference is positive 3. And then we'll go ahead and use that to figure out the 25th row. So remember, you can use either of these points when you write your equation and then use it to find the 25th row. On the test, we're just going to be grading to make sure, did you use one of the models that we've learned? Did you plug in? You're not just calculating in your head to find the common difference. You should be showing that work and process on your paper and then writing an equation that you're going to use. So to find the nth term, I'm going to use my a sub k. So I'm going to say we had 31 seats and it's adding 3 each time, and we're going to have n minus 5 since I'm starting with the 5th row. And then I can use this formula. I can leave it as is. If we wanted to get this into like a more slope-intercept form, we could of course distribute and combine like terms, but not necessary. Our goal here is to find the 25th row. So 31 plus 3 times 25 minus 5. So just a reminder, it should make sense to figure out the 25th row. We take the 31 seats from the 5th row and we add 3 20 times to get there. So we're going to add 60 and see that we have 91 seats. Hey, no calculator or rounding needed there. And again, we may not always want to box our answers as we prep for the AP test. I know you probably have heard that some, but for now, I wanted to make sure you knew what the answer was. So hopefully this has helped. It looks like we've definitely had practice writing formulas, using formulas, as we describe the patterns for geometric and arithmetic sequences, an extension of what we did last class. We looked at the patterns and what the rate of change or what the change is going to look like if a function is linear versus exponential versus neither. And so now you just need to practice. So make sure that you're completing your DP, any practice available, and ask your teacher if you have any questions.